Hi, my name is Sergii and I work at my news company, and this talk is about server-side JavaScript. One second. Okay, this talk is about server-side JavaScript, and it includes some low-level technical details, and it also about open source project, which is called Runtime.JS. And Runtime.JS is basically an operating system kernel built on a V8 engine, which means that this system boots directly on hardware, and it uses V8 engine by Google as a core component of the system. And it's basically the system is the one that optimized to run JavaScript applications. It can execute JavaScript only, and it doesn't support binaries. And it has a non-blocking and asynchronous I/O model built from the ground up. And also it's built from scratch and supports x86-64 architecture, and is inspired by Node.js. So what's the problem with existing systems when we use them to run JavaScript applications? And I think that mainstream operating systems are not the most efficient platforms for JavaScript applications. And the reason for that is because they designed it to solve different problems. They designed it to run compiled binaries and not just JavaScript code that runs in a VM. And they are also too complex. They introduce too many architecture layers and provide mostly inefficient APIs. And most system calls block, which is a problem when we use in JavaScript. We want everything non-blocking and in an event loop. And another problem is that event notifications require some very complex mechanism like polling, when we need to call kernel in a loop to get the new data. There is no central mechanism that lets us to be notified about any kind of event. And because of that, each application needs to implement its own event system and use file descriptors to get the data. Also, it uses unsafe C language at the core, which means that it's a security issue, and buffer overflows is a serious problem that can compromise the system. And they're written by C programmers to run C programs. That means that if we want to run JavaScript, we need to convert between C structures and JavaScript objects. So there is another layer between those for it to work. And let's see how software stack looks like when we run a node on Linux. On the bottom, we have hardware. On top of it, we run, of course, kernel. It's Linux, for example. Linux provides us with system call API. On top of it, we run a process, which is Node. And Node uses libuv and thread pool to provide an asynchronous API for the main thread. On the main thread, we have an event loop. And on the main thread, we also run an isolate, which is VM V8 instance, which has its own heap and garbage collector. And on top of that, we have a JavaScript application. So these three layers are here to provide some kind of isolation. For example, system call API isolates kernel from the user space application, so they cannot break the system and cannot directly talk to hardware. And the process isolates applications from each other. So, for example, Node application cannot directly access other applications' memory. And then we have an isolate, which isolates JavaScript application from the rest of the system. And these two components, which are libuv and thread pool, provide us with an asynchronous API. Let's see what process isolation is. It's a system that protects kernel from applications, protects applications from each other, and it requires to use an address space for every process. Address space is basically a range of memory that process can access. And this requires to use context switches. Because we have multiple address spaces, we need to switch between them when we're doing multitasking. And also we need to switch between user mode and kernel mode. And this adds additional overhead. We also need to use system calls because kernel is isolated from a user space application. But let's see what VM isolation is. Because JavaScript is a safe language and V8 compiles JavaScript into trusted native code that is guaranteed to be correct, and it will not access random memory and modify some internals of the system. Because JavaScript guarantees that you can do this from JavaScript directly. And because it basically creates a sandbox where VM controls everything that program is allowed to do. And it's often called software isolation because it doesn't use hardware mechanisms to enforce those memory restriction rules. And so what's the difference? We have two mechanisms that we use, and we basically paying twice when we're using both of them. JavaScript VM provides everything that process isolation can offer us for our JavaScript applications. We generally don't worry that when we run basically two tabs in the browser, one tab cannot break or change data in another, even if they run in the same process. So V8 VM can provide this isolation, and we basically don't need the processes to restrict the system from the kernel. It's required only for native untrusted code. So the Runtime.JS is a kernel optimized to run JavaScript applications. And it uses some optimizations that are not available for general purpose kernels. First of all, it's a VM isolation protection system that general purpose kernels use processes instead. And we can also provide a JavaScript optimized kernel interface that basically you can pass a callback to the kernel and ask it to call it, and it will work just like that. And we can also add communication between applications using JavaScript objects. For example, we can transfer array buffers, basically like passing a pointer between two applications. It's much faster operation when we don't have really process isolation. And kernel notifications can use event loop built into a system. And we can also write some kernel-side JavaScript, which might be useful in some cases. And so how does JavaScript kernel look like? So there is no binary support, there is no processes, no process isolation we no longer need, and no POSIX interfaces, and also no system calls. But instead, the system has software-isolated applications that are called isolates. Everything runs in a single address space. It has a built-in V8 engine, and all I/O is non-blocking and asynchronous. And also, the system has built-in global event loop for the whole system. And there is a lightweight threads for preemptive multitasking. So let's see how software stack for Runtime.JS looks like. We have a hardware. On top of it, we have a kernel. Then we run a system event loop, and on the top of it we have isolate VM instance that already provides all the security guarantees that our JavaScript application cannot touch hardware or break the system. And this is how architecture of Runtime.JS looks like. There is some native code that implements low-level kernel services, and it's also a V8 engine. It also exposes kernel APIs, and those low-level kernel services, it's something like memory management, I/O, interrupts, timers, initial RAM disk, scheduler, etc. And everything else is built on top using JavaScript. And high-level kernel services include device drivers and system services like network stack, virtual file system, and of course applications. So why would I use JavaScript for those tasks? Because it's already bytecode of the web, we can compile everything to JavaScript. It's very well tested. It runs basically everywhere. And it provides an easy way to write asynchronous I/O code. And it's powerful enough to write system components. We have typed array and array buffers that are very useful for handling binary data. And it's very safe and secure. It's built in a language that it doesn't provide a way to access, for example, random memory locations and write to them. So we are very safe with this and can use it for writing drivers and other applications. And actually, the device drivers are the software that basically does I/O code. So basically, it reads from a network card and passes data to applications. So it's very I/O-heavy applications. And it's perfectly, I think, reasonable to write them in JavaScript. And so there's software-isolated applications. We don't have processes. There is just isolates. And each program runs in its own isolate. And each isolate has its own garbage collector and heap. And we have an inter-isolate communication using remote procedure calls. A global event loop in a system, there is just one event loop for the whole system. And but at the same time, each isolate has its own execution stack. So basically, it's kind of like threads, but event loop controls and switches between stacks. So it's possible to interrupt long-running JavaScript code. Like what this function for can block the system, but if we use a stack for each application, we can just interrupt it and continue to with other applications. So this is how it works. For example, we have 3 isolates. Each one has an event queue and isolate stack. The system starts executing callbacks from the isolate 1. It's callback 1, it's callback 2, then callback 3. Then it switches the stack to isolate 2 stack and executes those 2 callbacks. And if, for example, callback 2 takes too much time, we can just switch the stack and continue executing the callbacks from isolate 3. And there is inter-isolate communication that's implemented and remote procedure calls. It basically lets call functions across isolates. And it's built on JavaScript promises. So this is the example of how this works. For example, we have function add, and we can call it from the other isolate, and it will return promise. Because there can be, because we need a synchronous call. Another example is asynchronous function call. In this example, we resolve promise in 2 seconds and return it. So, and when other isolates call this function, it can just use this promise to output hello world after 2 seconds. And another example is zero copy array buffer transfer. We can, because we don't have processes, we can just pass this array buffer without any copying. And it's very useful when we want to get data from, for example, from a network device. It can just pass the same buffer that a network card writes to, just to our application. So it's much more efficient system. And we can also pass functions that will return promise on the other side. There is also an isolate API that every isolate can access. It's a data environment, some system services. There are functions like exit log. And OK, there's a demo I'd like to show. So let's boot the system. So it loads. Oh, you can see it. So this is the system. It boots into terminal. We can type commands here, basically ls, for example, and it outputs a list of the files. So as you can see, those are all JavaScript applications. And ls.js is here just a simple application. We can do like echo, hello, and it will output our string. We can also do some other tasks like, for example, eval. And here we can evaluate some JavaScript. And it all runs on QEMU virtualizer. Can type exit. There is also some network support, and we can resolve, for example, host names. Like, let's do host. Well, it resolves host name, and this network stack and the device driver are both implemented in JavaScript. Like Runtime.JS.org. Okay, so, and what else? We can see the devices, PCI devices, for example, on our system. And let's exit. So power off. And another example. I hosted Runtime.JS on a server, and you should be able to connect it, and it should respond with UDP packets. So if you try this in command line using netcat -u runtime.js.org, port 9000, and type some text, and it should return this information. Let me see. Hello. Oh, it returns hello message. And it shows my IP address and source port. OK, now I can SSH to the server. Open the screen. And you should be able to see your error message. Yeah, it works, I think. OK, so let's continue with the presentation. So the project status is, it is an experimental project, and it's in development. It's not ready to use. It lacks many important features, and most APIs will probably change. And right now it targets mainly KVM virtualizer, so it's much easier to support its device driver, and we can run it on top of Linux. But of course, for the best efficiency, we would like to implement maybe native real hardware drivers. Not native, just real hardware drivers. And so why would you use this system? Because it's a network-first server system, and it provides safe environment. It has a sandboxed applications. It uses asynchronous I/O everywhere, and it's full hackable JavaScript. You have full control over everything. So basically, if you would like to implement your own file system or network protocol, you can do it in JavaScript, and it's much easier to work with it. And it's pretty small. It's less than 10 megabytes, and it's actually around 8, and V8 is 7 megabytes from it. So I think the future work would be to support TCP and HTTP protocols, add some file system support, because right now it's just read-only file system, and optimize internal structures, and maybe at some point lock APIs and support other virtualizer like Xen, so we can run it on Amazon. And about Node, it's not compatible with Node. It provides a lower level API than Node. So it might be possible to port a Node on top of it, but Node uses really Unix APIs, so there needs to be an additional layer that will convert those calls. And maybe we can even use an NPM as a system package manager. So there are the links. You can find the project on website runtime.js.org and on GitHub Runtime.js runtime. Also, thanks Mike for supporting the project, and thank you everyone. If you have questions, I'd like to answer them.